So here we have a theorem that is going to help us to verify using visual verification that last example that we looked at with sets of 1 or 2 vectors. So in this theorem, it's telling us that if a set contains more vectors than there are entries in each vector, then the set is automatically linearly dependent. So in other words, a set of vectors, say vectors v sub 1 through v sub p in Rn, is linearly dependent if p is greater than n. So if the number of unknowns is greater than the number of equations. So we need to prove this statement so that we can take advantage of it. So let's go ahead and suppose that we have a matrix A defined by the column vectors vector v sub 1, vector v sub 2, all the way to vector v sub p is a matrix in Rn. So let's think about, what is this telling us? What do we know about this matrix simply by thinking about the definition? Well, if A is defined by the column vectors v sub 1 through v sub p, and this matrix exists in Rn, we can say that A is a n by p matrix. So in other words, there are n equations, or rows, and there are p unknowns, or columns. So what I want to do now is let's go ahead and assume that the number of unknowns is greater than the number of equations. So if p is greater than n, or in other words, what this is saying is that if the number of unknowns is greater than the number of equations, what do we know is going to happen in this case? Well, if the number of unknowns is greater than the number of equations, this means then there has to be at least one free variable. So then at least one free variable must exist. And if one free variable exists, what does this tell us about the homogeneous equation using this matrix A, or the vector equation? It has a non-trivial solution. So if a free variable exists, then the homogeneous equation, or your vector equation, has a non-trivial solution. So therefore, by definition, the set of vectors defined by the columns of matrix A form a linearly dependent set. So you can make our final statement and say, well, therefore, by definition, the columns of matrix A so the set of vectors v sub 1 all the way to v sub p form a linearly dependent set by definition. Oops, we did it! Woohoo! And that is the end of our proof. So let's now take this newly verified theorem and use it to revisit the example that we looked at in the very last video. So to help us really see the power of this theorem, let's revisit a previous question. So at the end of the last video, I posed the question, is the set containing the vectors w, u, and v, or u, w, and v, is this linearly independent or linearly dependent? And we weren't able to use visual verification because the set contains 3 vectors. But we can now use this theorem as a shortcut to check what the relationship amongst these 3 vectors is. So here we go. Let's suppose that a matrix A is defined by these 3 vectors, vector u, vector w, and vector v. So we have this 2 by 3 matrix, we have 2, 2, -2, 3, -1, -1. Beautiful. So by definition, we know that matrix A is a n by p matrix, where n is the number of rows, 2, and p is the number of columns, 3. So we can also think about n being equal to 2 as the number of equations in this linear system, and p being equal to 3, we can think about this as the number of unknowns, the number of variables, or those weights. So, looking back up at matrix A, we can highlight at most 2 potential pivot positions. Or in other words, 2 of the columns in matrix A can contain basic variables. So we can say that at most 2 columns will contain basic variables. However, we can't forget about the third column. So while at most 2 of these columns will contain basic variables, we still have 1 column that contains a free variable. And we are assuming, again, that we have 2 pivot positions here. They're going to be at most 2 basic variables. But even if we have 2 basic variables, 1 free variable still exists. So the homogeneous equation has a non-trivial solution. So we can say that, therefore, since we have 3 unknowns, which is greater than the 2 equations of this linear system, the set of vectors defined by the columns vector u, vector w, and vector v is automatically, by definition, linearly dependent because a free variable exists. Woohoo! So this is a nice shortcut that we can keep in mind as we're determining the relationship amongst a set of vectors. You just want to be careful that this only holds true when the number of unknowns is greater than the number of equations. So if I gave you something like, if we suppose that a matrix A is in R4. So let's suppose we have a matrix in R4, and I give you a set of 3 vectors, and I ask you, is this set linearly dependent or independent? Well, we don't know. We have to check. We would need to check here, and this is because A is a 4 by 3 matrix, meaning that the number of unknowns is less than the number of equations. We have 4 equations and 3 unknowns. So it could be either linearly dependent or it could be linearly independent. We won't know until we check.